I just talk about the thing we need. As I said, okay, we care about finite dimensional vector space because in finite dimension, this representation theorem is true. In infinite dimension, crazy thing happen. So therefore, we have this thing is an inner product. Okay. So basically, we always consider R. Okay, I almost forgot. We don't care about this. So we always care about R. And then that means Rn times n. It's the same for tensor. So you can keep going on. It doesn't matter. So because they are the same, so we mostly just talk about this. Then once we have this as our set, or we call it a field, okay? That means we have plus, minus, multiply, division, and then lot of algebra rule. That means A, B, C is a A, C, B, okay, associative, those kind of things. Okay, we don't care. We assume they are true, okay? Then what? We now have something called vector space, okay? I just give you a revision. Again, this is review, so we don't need to worry too much about the details because we are not studying them. We are just reviewing them. Because for those who study them, then we need to prove, for example, a vector space has bases. Now we don't. So we have a vector space. What is that? That means we have something called addition, there's something for multiplication, and then what? You have a bunch of property that is true for the definition of vector space. That means something like this is, right? And then there are lots of things. These I assume you know, and these I assume you know. And the important thing is then is the basis. Okay, so basis, that means any vector space as in a basis. So m equal b1, b2, bn. Okay, the number of these that is linearly independent. This thing have a lot of things we call what is span. Span is subspace. Okay, this is basically a subspace of the n-dimensional space. And the n here is what? It's the number. It's the number here, right? If they are linearly independent, then this is the dimension, right? And then if we collect all this, B is a matrix B, B1 up to Bn, then this n is the rank, right? So, or column rank. And then there will be theorem saying that the column rank is the row rank. And then full rank means they are linearly independent, and then it links to B have inverse. And then it also links to B have n non-zero eigenvalue, blah, blah, blah. Okay, these are all the basis things. But one important thing here is that we have the standard basis, that is E1 up to En, which is what? Which is 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on, 0, 0, 0, 0, 1. Okay, now these are very trivial. Then you may ask why I'm talking about this. Because this thing can be seen as directional derivative using the EI on my fx. So that means this thing in the ith component is the same. So in other words, what is gradient? Gradient is defined as directional derivative of a f where the direction is the standard basis. This is why we need linear algebra to go to here. Because we use this so that we can do this. This thing leads to the following. This is why we have this, okay? Because this leads to 1, 2, right? Which is just, I repeat this many times. So this is directional derivative at E1 fx, directional derivative E2 fx, blah, 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 blah. And if you simplify the math, which I will talk about later, this one gives you the first partial derivative, this one gives you the second partial derivative, and this is why we have this expression. And this then can generalize to matrix derivative, or derivative with respect to a matrix. So that's why we start everything with this directional derivative. Okay, this is like it. And therefore, basically this is just a recap of what we need to know. I assume you know what is matrix, what is vector, what is inverse, what is determinant, that kind of thing. Okay, so these are just standard things. And then of course, what about norm? Okay, Frobenius norm, Euclidean norm. So these are the standard things. I assume you know. Okay, that means what? UV is just UV. Okay. In books, usually they want to go very abstract. They will say we're talking about a vector space, abstract vector space to some Rn. But for us, this vector space most of the time is Rn or Rmn or whatever thing. Yeah, because it doesn't matter. The thing is matter if we're working on very special structure. I now give you an example. There's a thing called Archian geometry that what? Their vector space live in simplex. So what? That means in this funny geometry, all the vectors are n-dimensional vector, but they are all larger than 0 and their inner product with 1 is 1. It's less than 1. That means what? That means in 3-dimensional case, let's draw a picture. This is 3D space. Okay, if we consider R3, this is our vector space. But in Archisan geometry, they only allow this green thing. That means what? That means they are not living everywhere in the cube. They are only allowed to exist in this plane. Then what? This plane is a space. It forms a vector space. Then because you want to make sure the vector space definition is correct, that means, for example, closure, that means two vectors u and v, you do something, you don't leave the set. That means in this case, they have to have funny addition. So in this Archisan geometry, the addition is quite interesting. It's not the addition we know usually, and similarly, they also have funny multiplication. So for classical or Euclidean geometry, we know that alpha times a v is just basically scaling everything by alpha. But in this funny algebra, this is not correct, because if you, let's say alpha is 9,000, then your point moves to here. Then it's not in the plane. Then it's wrong. So in this funny Archisan geometry, they have some funny u plus v and some alpha times v. So in Archisan geometry, vector addition is this funny thing. So that means what? That means if you have b and d, if you add b and d, in the Euclidean sense, you leave the triangle. But if you do it like this, you stay within the triangle. So, okay. And then your multiplication is something funny, like this. And then what? You have inner product is, okay, log. So what I'm talking about here is that all these things are what? Are also a vector space. But they are addition, multiplication, inner product, and also this is what? This is basically their basis decomposition or vector space representation. Also holds true in the framework. But for us, unless you're working on this funny thing, then we don't really care. Okay? So my point is, do not just think of it as a Rn. If this is the algebra or the geometry for the vector space, then everything we talk about on directional derivative, Gateau or Frechet derivative also works in that funny algebra. We just need to make sure the addition is using the algebra there, the subtraction is using the algebra there, the division is using the algebra there. So everything works. But normally, we just care about the standard one, that is Rn. And why I'm talking about this? Suppose I want to do optimization and I want to restrict my point inside this region. So what I can do? I can cast this green thing as a constraint. And then I do everything in Rn. Then I don't need to worry about this. But you can actually also do optimization, saying that I don't want to have projected gradient descent. I just want to do gradient descent. By what? Now I make sure always when I do gradient descent, the point never leaves the triangle. And I force this to be true by changing the algebra. Then I just do everything using gradient descent, but I change the algebra. Then everything will change because you change the algebra. But if you can show that this algebra is a vector space, and you have all the norm inner product, then everything is the same. You just change your number system to some very strange thing. And similarly, we are talking about R, right? What happens if we use complex number? Then you have some rule to make sure that everything here is true for the complex number. For the complex number is as long as if we do this instead of the classical partial derivative, then everything carries over for complex number. So in other words, yeah, this is what I said yesterday, right? We don't care about Cn, we just think of it as R2n, done. But you can also say, no, I don't want to do R2n, I want to do Cn, because if my n is very big, if I make R2n, it's 2 times bigger, my n is already very big, if I make it 2 times bigger, then it's even more difficult to compute. So I want to work directly in Cn, then I can do all the gradient descent, and I make the dimension half. But then I need to make sure the partial derivative is correct in the complex world. So I just need to change this thing, and then everything carries over. So the whole point here is that this kind of thing looks very naive, looks very innocent. No, because they are true in a broader sense. Broader sense means you change the geometry, you change the algebra, even you change the number system. Okay, maybe this is also true for p-adic number. Okay, so maybe this is true in p-adic, and maybe we can do some crazy thing. Or maybe this is true in fractal dimension, then yeah, there will be some funny thing. That's my point. These are abstract things, so that means do not restrict your viewpoint only to Rn. But we mostly will work on this, so therefore it will give you an illusion that it is true in Rn, but actually it's also true for many other things. So that's my message. Okay. So now this is off track. Come back to the main thing. So now what? These are the linear algebra thing. So as I said, it's just a recap. So I'm not going to go too deep, and I'm not going to do everything like because of this definition we have this theorem, or and we have this corollary. No. If you forget some linear algebra thing, then when we use it, we go back to have a look. That's it. So that's just a recap. Then what's the next thing? The next thing is, okay, topology.